So, cargo cult science, what is this all about? It goes back to a famous speech Richard Feynman gave back in 1974 in Caltech. And there he coined this term cargo cult science. It's here you have the citation for this publication. And to just define what he called cargo cult science, this is a form of alleged science that follows all the obvious signs and forms of scientific research, but lacks something essential. And this something essential is the scientific integrity, the honesty, the rigorous questioning of one's own results and explanations, and the disclosure of all relevant information to the best of one's knowledge and belief. Just to briefly mention that, I recommend everybody to just have a read of this speech given by Feynman. It's quite a nice read. And there you find some more about cargo cult. So I don't go into any further details of the cargo cult. This is more something from, let's say, the South Sea and results from Second World War and people first exposed to the Western world and not realizing what's going on, and then afterwards, when the planes were no longer coming and providing them with nice stuff, they tried to set up everything in a way that the planes will come back, but they don't do. And so basically that's his idea, his parallel, that he says it looks like they do everything fine from the outside, but they don't really know what made the planes land in the first place. And so this for science, this means research can appear scientific, but have neither scholarly contribution or impact. And the important thing for me is that I learned in my time in science, all the last about 2 decades now, is that science is about quality and not quantity, and it's about semantics and not metrics. So that's just a bit for this first term, cargo cult and cargo cult science in particular. And you might see here, and you will find that out, that I have this impression that what we call research data management sometimes has this tendency to be one instance of cargo cult science, and this utterly misses the point. So we need to deal with research data in a sensible way, and you will find out during the next few minutes that this is something that's not new at all. So now for the provocations. First, my very personal take on research data management, and this is a series of in total 9 statements. I'll just read them here, and it's probably something we can discuss then in more detail. Just to mention that briefly. Afterwards, I will put all these slides on Zenodo, and the link to the Zenodo will be with a recorded video. So just that you will have time to read through with more time. So the first statement: research data is an underdetermined term with many meanings. Without shared understanding, management will never succeed. So the first thing is we need to define what do we mean with research data. And this is not something where you can say, okay, I have the one and only definition for research data depending on your field. There is many different definitions of that. And the more interdisciplinary you are, the more you will realize there is just no one definition that fits all. The second statement: research data are only the basis of empirical sciences, but they have no value in themselves, nor are they worth preserving per se. So there's no point in just preserving our research data just because they are data. That's something to have in mind. A third statement: research data management is nothing new. The traceability and reproducibility have always been and will always be key aspects of the scientific method. Research data management has nothing to do with digitization. It's another thing. So research data management was important in the past as well as it will be in the future. Digitization makes it only more urgent due to us having way more data than before. And even thus, this I get drowned in data is nothing new. Just go back to the 17th century to the first scientific publications. You will have the same lament there that, oh, there's too much of information. I can't process that all. So that's nothing new, and that's nothing that's new in the digital age, basically. Creating or acquiring data has become incredibly cheap. And our problem is that we lack strategies how to properly deal with all the data we accumulate. So it's much easier to recreate data usually than to find the right piece of data that we've recorded once. And this is just not sustainable in many ways. Most scientists are not able to reproduce analysis of their recent publications nor provide the underlying data. You may prove me wrong, and I would be happy to be proven wrong. This is just my personal experience, and I'm not really somebody who is kind of different here. So you can happily go to one of my perhaps a bit older publications, and I will have the same problem. But I see that as a real problem. The responsibility for research data management usually lies with the individual researchers and not the institutions. So that means that there will nobody be there about they can say, oh, please manage my research data. No, it's you as scientist who is responsible to do that. And this is in particular because you are the only one usually who really knows about the data and can answer all the relevant questions. There is, of course, aspects that institutions have to take care of. But most of the time it's you and not somebody else you can just dump all the all the work to. The second last statement, many people confuse the tool with the solution. An ELN is not a solution. In best case, it is a tool. And you can do that with all the other nice tools that are there around. And solutions emerge, at least in my experience, from the competent use of the appropriate tools. And which tools are appropriate is always a matter of your local context. And the last statement, research data management strategies focus mostly on metrics. So one of these famous things is the quantification, how fair your data are. Oh, that's just useless. Metrics are usually useless. In the same way useless as if you would say, okay, somebody's only good scientist if he publishes more than 10 papers a year. What bullshit. Data quality is a relevant aspect, but it's hard to measure and it's even harder to ensure. As I mentioned, the FAIR principles, you all probably are familiar with the FAIR principles: findable, accessible, interoperable, reusable, and I recommend everybody to read at least once in detail this first publication, the foundational publication, and have an idea what their background is, because it makes it quite clear. And most people that I speak to in the research data management community seem to not be aware of the real origins of the FAIR principles. And in biomedical imaging and as a prerequisite for training machine learning algorithms. And not the first, but the last author and corresponding author of the FAIR paper from 2016, Barend Mons, he published 2020 in Nature a comment, and he made it absolutely clear that FAIR is about fully AI ready. So let's just look into what I think are the problems with the FAIR principles. They entirely lack a focus on the quality of data and therefore on data curation. Interestingly enough, in German it's called Rat für Informationsinfrastrukturen. They published recently a longer white paper where they unfortunately only in the German version clearly say in the appendix that FAIR doesn't say anything about quality of data. In the English version, you don't find that statement. A next point is data are only the basis for scientific insight. Data are not insight in themselves, and at best they're the basis for scientific insight, and there's no point in just publishing all data. This is basically a denial of service attack on the scientists. They're then drowned in data. What you need is qualitative, high quality data, and you need insight and results. So therefore, publishing research data is just not an end in itself. I have another problem with the publication of the FAIR principles themselves. This publication entirely ignores the work of the predecessors and is hence in itself unscientific. And just briefly mentioning that my problems I have with artificial intelligence and machine learning in science is this is a tool, but it doesn't give insight itself. The next thing is that it can only operate on accessible data, usually digital accessible data. Whether these data are representative is a question nobody seems to ask, or nearly nobody seems to ask. And just the last point, well, you can say, okay, that's obvious, but even though it's pretty obvious, sometimes it seems to get forgotten. It only provides correlations, no causalities. And that's, of course, a clear difference. A few words about big data, and this is a quotation or it's a quote from a book I really like, Christian Borgman. It's really a great book because she thought through the things, and she says scholarship and data have long and deeply intertwined histories. Neither are new concepts. What is new are efforts to extract data from scholarly processes and to exploit them for other purposes. Costs, benefits, risks, and rewards associated with the use of research data are being redistributed among competing stakeholders. The goal of this book is to provoke a much fuller and more fully informed discussion among those parties. At stake is the future of scholarship, and this last sentence that I think is particularly important. And so the problem is if you rip research data out of their context, it's a major problem for gaining insight, because if you rip them out of their original context, well, you lack the context. You don't know what they mean and whether your interpretation is correct. And therefore, we as researchers are responsible to sufficiently document our data, but we are clearly not responsible how others will use our published data. That's their responsibility. Our responsibility lies in providing enough metadata for others to make informed judgments about our data. So what is research data management after all? First of all, it's a political phrase, and it's an empty political phrase lacking the necessary intellectual depth. And so very few research data officers, meaning data stewards, data architects, have sufficient personal experience to fulfill their role. My rule of thumb is you need to have a PhD and at least a postdoc and have to kind of felt and experienced yourself that you're just not fit for the job of really managing your research data, that you just didn't find the data you measured in time, that you have really experienced that yourself. And if you've done so, and if you have probably looked into a few of tools that might help you with that, then you have enough experience and are probably good for the job. The policy debate we have reveals a shocking ignorance of both the history and the realities of the situations. And I must say that programs comparable to the NFDI have already failed. Just look at the UK eScience initiative from 2000 to 2009. It's not much left there. And so a last thing that, well, we tend to constantly reinvent the wheel because it's such a great idea. But just reinventing the wheel and not learning from the mistakes others did due to be it ignorance or lack of knowledge doesn't help us to come to useful solutions of the real pressing problems. And the second thing I'd like to say to that is, so as a leitmotif, research data management is clearly a necessary, but it's not a sufficient prerequisite to gain scientific knowledge and insight. So research data management is clearly highly relevant to the quality of science itself, regardless of its use as political catchphrase. It's not a new aspect, as I mentioned already, of research science, and the increase in data research and digitality has just highlighted the widespread lack of structures and scientific rigor. And so the proper handling of research data is clearly an indispensable prerequisite for scholarship. So that's basically the answer to my rather provocative question in the title of this talk. And now the question, of course, is, and I try to be fast enough to, in the next 10 minutes roughly, give you a bit of an idea how to implement it in our research routines. And this is now a tour de force through a few tools and suggestions that I have basically developed with the help of a few others and very capable students and colleagues in the last 15 plus years. So the first is data provenance during data acquisition. The idea is we record data and we need to make sure that we have all the appropriate metadata at hand. This finally we managed after nearly 15 years of existence, or at least 12 years of its existence, to get it published. So what's the challenge is we need to record all relevant metadata during the data acquisition in a machine readable way. Why during data acquisition? Because that's the time where you know what the context is, where you have access to all that information. It needs to be independent of the vendor file formats of the operating systems and the network infrastructure. So you can't rely on your computer you record your data with to be connected to the even local network. The demands is it needs to be human writable and machine readable, with focus clearly on the human side, because it's the human task to note all these metadata. It needs to be sufficiently simple and elegant to use, so it should work well for an undergraduate student after, let's say, an afternoon of training. And it needs, of course, to adapt well to the changing requirements of science. It must be robust, modular, flexible, and easily extensible. And so this is what we came up with. It's a, you could say, a machine-readable, minimalistic electronic lab notebook. It's just a bare text file, and it answers all the 6 important questions: who has done what, with whom, when, how, and why. And what you see here basically is it's block-wise. It's block-wise that you have key value pairs, and you have always a general block: who did it when, with what sample, and you have always a block with comments. So the important thing is that you decide which information to acquire, basically. The actual format, whether you use this one or something else, I don't care about too much, as long as you get the information, you get it in a sensible way. So the key aspects: it's plain text, it's human writable, it's a file that resides next to your data, it's machine actionable, it has sufficient detail. And the key thing here is think of it as kind of a form. You could even print it out and write down all the things by hand and later on then transfer them to a digital file. That's not a problem at all. The key thing here is that this is kind of a form, so you never need to remember which parameters were the ones I forgot last time, because it's just in your format there, in your scheme. And it's, of course, modular and extensible. So I will skip here over. That's just an example how you can have a lot of different blocks for different methods, of course. I would go to the next part. This is data provenance part 2 during the data analysis. And the idea here is to have a framework that helps you to record in a gapless way everything that happened to your data, starting with the raw data and ending with the final publication, be it usually a figure or a table. So the challenges here is that we have a fully reproducible data processing and analysis pipeline, including a gapless protocol of each step. And the next challenge is that most scientists that I met have never received a formal training in programming, or let alone software development. So what are the demands of such a system? We would like to have a largely automated scientific workflow system, as it's sometimes called, that can handle larger amounts of data. Okay, large amounts of data is always, yeah, in the eye of the spectator, so to speak. I attended DEFNIF NFDI meeting earlier this week, and for them, large amounts of data is petabyte a year. For me, large amounts of data is hundreds of data files in 5 years. Again, it needs to be sufficiently simple and elegant to use, should work with an undergraduate student, and should adapt to the changing requirements of science. So this is a short glimpse of what we came up with. So what you see here in the top left is a text file again. This is a recipe. We call it recipe-driven data analysis. And the key here is that we usually have quite a clear idea what we would like to happen to our data. And so what you do here is you define simply the data sets you would like to operate on. This, in this case, is just a path on the file system, could be something else, could even be a DOI if you like so. And then you define a series of tasks that you would like to happen to your data. And you could even say, okay, this particular task should only operate on a certain subset of my data sets. And this this answers all the important questions here, namely who has done what, with whom, when, and how does it do that? So you write down this recipe, and then you call just one simple command with the recipe as a file name. And what then happens is that not only will all your data be processed in the way you defined in your recipe, but at the same time, another recipe will be written in recipe style, a full history. And you see here just an excerpt of that history. And the important part here is that you see all the implicit and explicit parameters included in here. And as I said, this is a fully working recipe. You can just feed it in again on top, basically. And so redo entirely your data processing. Key aspects, so the recipe-driven data analysis, no programming skills needed anymore. We have the data set as a unit of data and metadata that abstracts away from the vendor file formats. Full reproducibility, it's modular and extensible. It supports now already different spectroscopic methods. And you can, of course, if you find somebody who can program decently, you can just from the framework derive your own packages for other methods. I go here very briefly through. It's just the framework as such already has included, batteries included, basically a lot of things. There's for now, 2 different EPR methods available, UV-Vis, NMR. You can start to at least analyze solid state NMR spectra. There's a fitting framework that works well with that. And this is, I will skip here through, that's just what you can do herein. It's fully documented, so you will find all the details. And I would just like to come briefly in the end to the last and go here through as well quite quickly. So this all isn't enough yet. What we need is a modular digital research infrastructure and research data infrastructure. And this is just this idea, we called it Lab Inform, to make use of the tools available in the digital area. And this is a few things you have seen. The metadata is info file I've shown you, the electronic lab notebook I will briefly show you. So we need a repository for warm research data, as colleagues from the KIT nicely phrased it. So data that you can't yet publish, version control system, unique identifiers for everything in the lab, all that. And 2 things I'd like to particularly highlight is an electronic lab notebook that we developed in this context. Wiki-based, very small footprint, no database needed, and you find more information here. And this repository for warm research data, we call it data safe, that gives you access to your data using unique and persistent REDs, and has even functionality built in for checking your data integrity. And I'll skip over a few slides here by now. This is the beauty of using LaTeX for the slides, that you can do those things and come just to the summary. And so let's revisit basically the FAIR principles and the F, the findable. You can just, let's say in the small scale, you can make use of the FAIR principles if you really like so, and kind of interpret them in a different way and say, okay, findable means, do I know where exactly this one data set is located? I remember to have recorded and urgently need now for publication. And if not, would I have any chance to successfully search for it? This is the findable component. Accessibility means, do I have access to the data? Is it on someone else's computer, hard drive, memory stick, or beware at my old institution with me being in a position to, not in the position to phone somebody up and ask for help? Might be that there's just nobody you could just call for whatever reason. The interoperability, did I remember to export the data into a format I can work with without access to the instrument control software of this old device retired 5 years ago? Alternatively, far away or at my old institution, there's just no point in you being somewhere else and wanting to analyze your old data and realizing, oh, damn, I didn't export them into a format I can work with. And finally, the reuse part. And reuse for me is always kind of a very self-centered motivation, egoistic perspective. Did I record all necessary information, meaning metadata to answer all the questions I may have now with much more experience and context and for the first time really looking at the data. So this is how you could kind of interpret for yourself the FAIR principles. And here's a nice quote. Note that there's no way to email yourself in the past to ask for clarifications. A great book by Alessina and Wilms. So be fair to yourself and think of your future self. The key takeaway is here is the FAIR principles can be applied to your local context. I'd say you stretch it quite far from the original meaning of the FAIR principles of their original authors. However, you can do so if you like, and therefore, in this case, they really get useful. Reuse, first and foremost, means reuse by your future self, and so FAIR is a tool at best to ask and most probably and hopefully answer the right questions. With that, that's just the overview of the tools I've developed, as I said, with help of your very capable colleagues I had the pleasure to work with over the last years. The info file I showed you, Aspect I briefly showed you, LabInform ELN and LabInform I only mentioned basically. And with that, I'd like to summarize what you would hopefully take home. The traceability and the reproducibility are and have always been key aspects of the scientific method. The amount of research data we create increases exponentially. That's nothing new, but it's still there. And hence we need to develop strategies to manage these data. It's the same way people had to deal with that decades and even centuries ago, but it's not getting better in a digital age. We need to document in sufficient detail what we have done, and documentation needs to be automated wherever possible. Reproducible research taken seriously requires us to use a digital research infrastructure consisting of modular, robust, and interoperable and extensible tools. And it is my express view that, and I'm very convinced of this, that only systems that are sufficiently easy to use and whose use promises obvious advantages in the end will get used. With that, I'm at the end, and it's only time for two very brief slides with a bit of advertisement. The one thing is that in June, I'll be at the Chemistry Data Days in Mainz. Thanks for the kind invitation there. And then I'll give a talk that basically is a follow-up of what I try to do today. What is science and why should we teach it to scientists? It might be a bit of a philosophical title, and it connects clearly to what Feynman said in his speech about cargo cool science. And the other thing, starting next Thursday, there will be in German a lecture on research data management, so Forschungsdatenmanagement at University of Rostock, and that will be hybrid, so you can join that digitally. You will find all the details on the webpage to the lecture. And with that, I'm at the end and very happy for all of you to listen, and I'm happy to take any questions, and I'm looking forward to the discussion.